All right, we're going to go ahead and get started. I'd like to thank everyone who is joining us today. Welcome to today's CNCF webinar, Deploying Complex Stateful Applications on Kubernetes with KubeDirector. I'm Caitlin Barnard, Marketing Manager at CNCF, and I'll be helping to moderate today's webinar. I'd also like to welcome today's presenters, Tom Phelan and Joel Baxter from Blue Data. So just a few housekeeping items before we get started. During the webinar, you are not able to talk as an attendee, so there is a Q&A box at the bottom of your screen. If you have any questions throughout the webinar, please feel free to drop them in there, and then we'll get to as many as we can at the end. The session is also being recorded and will be sent out afterwards and available online along with a link to the presentation. So with that, I'll hand it over to Tom to kick off today's presentation.
Thanks, Caitlin. As Caitlin points out, Joel and myself are from Blue Data. Blue Data has spent the last 6 years deploying AI, machine learning, deep learning clusters in the enterprise. In full disclosure, we were recently acquired by Hewlett-Packard Enterprise, so we are now part of the HPE family. So today we'll be speaking about Kubernetes, and on the first part I'll review a little bit, talk about stateful versus stateless applications. We'll talk about how AI and ML and deep learning are complex stateful applications and how that has some challenges on Kubernetes. We'll then dig into what Kube Director actually is, a deep dive of the technology itself, a demonstration, and some takeaways at the end. So to begin with, I know this audience knows a lot about Kubernetes, but just kind of do a level set. What is Kubernetes? It's an open source platform for container orchestration. What this means is it's a collection of building blocks and services that allow containers to be placed on individual hosts following a set of rules. When we say host, we mean either a virtual machine or a bare metal physical host somewhere or a virtual machine in the public cloud. Top use cases for Kubernetes up to this point has been the deployment of stateless applications. These are also known as microservices. It's still an evolving platform for stateful applications, and we'll be talking about that today. When we say stateless application, what we mean is each application service instance is identical. So each container running an instance of a stateless service is identical to any other instance running that same service. They don't have a persistence or a configuration that is unique. Any information that they need to store and access is stored remotely. And when we say remotely, we mean that the persistent storage has a lifespan different than that of the container. If the container were to exit and restart, it could connect to the same persistent storage, the remote persistent storage, without loss of context. Typically, these sorts of applications are referred to as cattle because each instance is like every other instance of that application. This is in contrast to stateful applications. In a stateful application, there is some intrinsic difference to each instance of the application that's instantiated within a container. It may be as simple as an IP address, or it may be more complex. And this critical information is stored locally. Locally means it's part of the storage that's associated with the container when a container starts. The reason this is the case is that these applications that are considered stateful are not written in a cloud-native manner, cloud-native architecture, where the services, the running code, is separate from the storage itself. In the case of stateful applications, they are combined. Such applications are completely referred to as pets, since each instance is different, and the loss of one such instance is a loss. Now we look at stateful applications such as AI, machine learning, deep learning. These are some of the most stateful applications that we have in the enterprise today. What do all these applications have in common? They require large amounts of data, and that's okay. That data is typically remote. It's in a data lake external from the containers themselves. But these are complex distributed processing solutions. They are not written in cloud native architecture. They are typically deployed as collections of services running on a bare metal host or in a virtual machine. And those services have interdependencies. They are not a cloud native architecture, there's no microservices, and there is an application state. So these are some of the most complex stateful applications in existence, and they require special treatment. To step back for a moment, when we say we're running a Hadoop or an AI or a machine learning cluster like Spark or TensorFlow in containers, what we're talking about is deploying it the same way it's deployed on bare metal. This is not re-architecting or rewriting the AI or ML application. What I'm showing here are 4 boxes, which are the prototypical deployment strategies for Hadoop. There's a resource manager, there's a collection of node managers. They run different services. With containers, what we're talking about is putting each of those nodes into a container or potentially a pod with Kubernetes. And this entire set of containers is what's referred to as a cluster. So when we're going forward with the remainder of this presentation, this is what we're talking about when we're saying we're deploying a cluster of containers running one of these machine learning, artificial intelligence, or deep learning applications. With Kubernetes, we have a number of tools and building blocks to work from. These are called objects. Pods are a collection of containers that are deployed on an individual host. We have a concept of a stateful set. Stateful set refers to a set of features associated with the Kubernetes container that are necessary for running a stateful application. They order the services in the pod that are brought up. They preserve some state of the container itself. That is done with the use of persistent volumes. And each application that's deployed via a stateful set is done via an operator. An operator is a collection of actions that can be performed on a per application basis. Typically, operators are constructed from the use of a custom resource definition. You'll also hear the term CRD. Kubernetes operators are a basic API's way of packaging, deploying, and managing an application. Now, the open source community has created an operator framework, which makes it easier to develop an application-specific operator. And finally, there's another tool on top of that called the Operator SDK. These are layers of abstraction, which make it easier to develop an application-specific operator. But still, we require a different operator for each application to be deployed on Kubernetes. And with the plethora of AI and ML applications in the marketplace today, this would be quite a few operators. This is very challenging for the enterprise to do. So what do we need to do? There's got to be an easier way. And this is what Blue Data has done. We've used our knowledge and we're helping the community with an easier tool. Blue K8s, you might hear that term. This is an umbrella Apache project started by Blue Data, but now open to the open source community, focused solely on bringing enterprise support for complex stateful applications to Kubernetes. There'll be a series of open source projects in this case, and the first that we rolled out is KubeDirector. This is the URL for the KubeDirector site on GitHub. At this point, I'd like to turn it over to Joel for a deep dive into KubeDirector. Joel, you might be on mute.
Yep, I'm off mute now. Okay, so I'm going to start with the background that Tom laid there and dig a little bit more into the design of KubeDirector, the specific things that we're doing with it, and tempt fate somewhat with a live demo. It's a lot to get through, but I'll try to leave us some room for questions at the end as well. So if we're going to start talking about the specifics of what we're implementing in the KubeDirector project, one thing to get out of the way is our motivation for this project. You know, why would we want to create it? Why would someone want to use it? And maybe, you know, as an open source project, why would someone want to contribute to it? because there are a lot of ways to deploy things on Kubernetes. There's a lot of solutions for getting applications to run on Kubernetes. Tom mentioned app-specific operators. There's also sort of client-side template management solutions like Helm and Kubeflow. And if you're looking for a solution to deploy a particular thing, maybe in a production environment, you're probably just going to do a bullet point comparison of features. You know, does this solution do what I want it to do right now? But from our perspective as developers, and from looking for open source contributors and the direction of the project in the future, we're also interested in asking, what does the design enable us to do as we go forward? What things does our architecture of our solution make easy to do or hard to do? And there's not going to be a best solution for all possible purposes, but we do want to find sort of a sweet spot between two extremes of deploying applications on Kubernetes. At the one end, there's a very low level use of the Kubernetes APIs and kind of making a bespoke solution for every application when you figure out that you need to deploy that application. And on the other end, and this is where, for example, app-specific operators come in, some other person who's an expert in the application and in Kubernetes has put together a solution for you kind of as a black box, and it handles this application very well. But if you want to tweak it, or if you want to manage other applications, then it's not the best solution. So if we're going to aim for a spot between these two extremes, we don't want to just use the low-level, make our end users use the low-level Kubernetes APIs directly. So we need to build some abstractions on top of those to guide these abstractions, to pick what features and what data model and what operations we support. We need a focus. We don't want to go all the way towards just supporting a specific application, but we do want to focus on this domain of big data, AI, machine learning, data hungry, these stateful applications that Tom described. And so if we look at what these apps have in common from the point of view of what sort of behaviors we want to support and what sort of workflows are interesting, there's a lot of things that can guide our design. And so that's what we're shooting for with KubeDirector, and that's what I'm going to try to demonstrate as we go forward here. So KubeDirector itself is what's called a custom controller. This is a process that watches the Kubernetes API for resources to appear. So someone else uses the Kubernetes API to submit a resource, to create or change or delete a resource in Kubernetes persistent store. And then the controller notices that that has happened and does something. And in our case, we're actually watching, among other things, for custom resources to appear. So we're not just interested in observing the pods and the services and things like that that are the sort of native Kubernetes objects. We've also provided some schemas to Kubernetes to define some custom objects that are KubeDirector specific. And we'll talk a lot more about those in just a minute. And these are essentially the requests that end users provide to Kubernetes that are requesting KubeDirector to do something on their behalf. And so when KubeDirector sees this request, it's going to, again, start using the Kubernetes API to create stateful sets, create all these other objects that Tom mentioned to sort of try to bring the world into accordance with the user's request. Now, everything I've mentioned so far in this slide, this is pretty much what an app-specific operator does. So the way KubeDirector diverges from that is that the logic for determining how to respond to these requests, there's no app-specific semantics coded into KubeDirector itself. KubeDirector works with data-driven descriptions of application types, how you deploy these applications, how you manage them after they're deployed. And then it uses those descriptions, which can be provided by the end user. They don't have to be created by the KubeDirector team or anybody outside the user's organization. Those descriptions completely drive KubeDirector through a state machine of deploying and then managing these applications. So one obvious benefit to that is that it is there's a somewhat natural and easier process for bringing new applications into the fold of being deployable and manageable on Kubernetes, especially if you have an existing application definition and you just maybe want to roll to a new version of that application, use some different packages, set it up in a slightly different way. It's quite easy to make that modification in these metadata files that describe the deployment. But if you want to just bring a completely new, say, open source application in that maybe hasn't had an operator written for it yet, you can do that as well. you can create a new set of metadata and a container image for that application and give it to KubeDirector, and KubeDirector will know how to manage it. There's also a slightly more subtle benefit from this, which is that there's other objects and features that KubeDirector currently, and especially in the future, will support, which are cross-cluster and cross-application features. Things like how do you access data sources? How do you authenticate users inside your applications, maybe integrating with your enterprise AD server? How do you hook clusters together into processing pipelines or make clusters aware of other objects you defined? Once these features are implemented in KubeDirector, then by virtue of providing the metadata for a new application type to KubeDirector, it participates in those features automatically. And different applications, even from different developers, can participate in these features together without any knowledge of each other. So concretely speaking, KubeDirector is just a process that runs likely on the same Kubernetes platform that it's managing. Typically, when you deploy a controller, you're just going to have some sort of deployment YAML or JSON file that describes, hey, here's the container image to use. Maybe pull an image from Docker Hub or from your own internal image repository, and just deploy this on Kubernetes. It starts listening to the Kubernetes API, and it's basically ready to go at that point. Then an end user who wants to actually deploy a virtual cluster comes along and provides this custom resource that I mentioned earlier, this specification of the user's intentions. They provide a document to the Kubernetes API that says, I'd like a Spark cluster, for example, and here's a description of the resources it needs to use. And Kubernetes takes that document and just stores it into its persistent store, into etcd. So even though Kubernetes has been told about the schema for these resources, it doesn't treat them as having any implied actions. It's just a document that Kubernetes is managing. So you use a standard Kubernetes API client to create this resource. KubeDirector then notices that the resource has been created and that it represents a request to create, say, maybe a Hadoop cluster or a Spark cluster. And then it enters what we call the reconciliation loop. The reconciliation loop is basically just working its way through a state machine where it instantiates some objects in Kubernetes. It takes some actions on the Kubernetes API. Maybe it creates a stateful set, maybe it creates a service, and then it goes away. And then it comes back in a little while to check to see, has this been completed? If so, it'll go to the next part of the state machine. So maybe it has to set up a pod, wait until the containers are ready in that pod, then configure the application inside the pod. So there's a set of steps it has to work through, and meanwhile, it's updating this resource that the user provided to say what the status of this process is. And then once KubeDirector is finished working its way through the reconciliation loop, the cluster is up and ready to go. By using this custom controller approach, and also by taking a data-driven approach to implementing support for different applications, one of the good things about the KubeDirector design is that it doesn't require, but it supports a separation of concerns among different user types. So if you have people in your organization that have different knowledge sets, maybe different privileges to do different things, by virtue of the fact that everything we do runs through the Kubernetes API, uses custom resources, and is controllable by all the authentication and authorization methods that Kubernetes provides. So for example, you can say these users in this namespace have privilege to create or modify these custom resources, and these users in this other namespace have these different privileges. You can have this separation of concerns. You can have application experts who are entirely responsible for figuring out how to create the container image and the metadata for the application. But they don't have to have the privilege to install this application in Kubernetes. They don't have to understand how Kubernetes operators work. They don't have to write Go code. They just have to know how to write to this metadata format and make a container image. Then they can supply that to an administrator, either like an IT kind of administrator or maybe a project manager, who can take this metadata and import it into KubeDirector and determine which users have privilege to make instances of this application. So essentially they're setting up a policy or a template for different sets of users. And then the end users can come along and again, they don't have to understand how operators work. They don't have to know the details of the application or even which container image it's using. They just know that here's a kind of application that's available to me. I can submit a request to Kubernetes to instantiate that application. And maybe there's various knobs and controls available to the end user, like selecting the amounts of resources it's going to consume or selecting which services it's going to run. But whoever designs the application for deployment at this particular site can dial that complexity up and down. They can decide how much complexity is actually put onto the end user. And from our perspective as Kube Director, we just want this custom resource from the end user, this request to instantiate an application, to come to the Kubernetes API, and then we'll tackle it. We don't really care where it comes from. This is probably a very rich area of development for putting a nice user interface on top of this part of the workflow. So thinking about that design, that architecture for Kube Director, let's call back a minute to the motivation slide. Why would we want to have a solution architected like Kube Director as opposed to some of these other things that are available to us currently? And again, these other things are very good solutions for many use cases, but Kube Director, we're trying to make it strong for some particular use cases in this domain of applications. So one thing, as I mentioned, is that we support these distinctions between user roles. You don't have to have a power user who knows a lot about Kubernetes and the application, or someone who has privileges to do very high-level privileged things in Kubernetes, as well as deploy the clusters for the data scientists. You can separate out these roles. And if you're using a more client-side templatized approach, this is harder to do. It's not impossible, but there's a lot more work to make it happen correctly. Because we're sort of sitting behind the Kubernetes API, because we wait for documents to come through the Kubernetes API before we react to them, we get the benefit of all the authentication and authorization methods that Kubernetes provides. And we don't have to worry about having maybe two different sources of authority about users that might have to be kept in sync with each other. If you're using a solution like Helm 2 with Tiller that sits out in front of the API, where you authenticate to that other solution first, and then it sort of acts like a super user to Kubernetes, then you don't have that benefit. There may be reasons you want to do that approach, but in many cases it's more natural and more easy to keep secure if you just have this one authority of user privileges. Also, because we have this process that runs, that is long-lived, sitting in Kubernetes, watching these deployments after they're created, we're not just intervening at deployment time. After the cluster comes up, we can watch it to respond to further user requests to scale it up and down. We can respond to auto-scale policies to scale the cluster according to load. We can auto-remediate when there's errors. When a stateful node goes down, there may be application-specific things that have to be done to bring it back up again. All these things require having a long-lived manager process there to watch it, because these are semantics above and beyond what Kubernetes can understand or can be made to deal with. And so again, if you're using just a purely client-side sort of template-driven approach, you don't have this long-lived manager process to take care of these things. Now, all those things on the previous slide, all those benefits also apply to application-specific operators. There's a couple of other ways in which Kube Director is different from application-specific operators, and we've really either explicitly or implicitly hit this point a lot up until now. And that's because we are data-driven by metadata, by documents that describe application types. It's easier to import new applications to be supported by this solution, and you can have common features that apply across multiple application types. Now, if you are a single application shop, or if you have a small number of applications that already have well-developed operators for them, this may not matter to you, but otherwise it might. Okay, so the rest of the talk, we're going to be actually looking at Kube Director in action and talking about some details of the way it does the things it does. Just to make sure that we have everybody on the same page, I'm going to cover a few bits of concepts and terminology here. This orange cloud in the middle of the picture, we may get some other slides later on that use this same sort of iconography. That represents just all the resources that have been created in a Kubernetes site. So all the documents, all the native Kubernetes resources as well as the custom resources that we've defined. When someone asks KubeDirector to create a virtual cluster by submitting this custom resource that asks to instantiate an application type, KubeDirector is going to start creating objects in Kubernetes. And one of the important things that you'll see when we get into actual KubeDirector activities is the concept of roles. These squares inside the deployed virtual cluster there, those are each a container acting as a virtual host. Like Tom mentioned, our approach to deploying these stateful applications, kind of a model that we're able to fit on a large group of applications, is to treat each container as an entire virtual host. It has a file system, it has a network identity, it has services running in it on the standard service ports, multiple services inside each container. And within this virtual cluster, among these virtual hosts, we use the role concept to distinguish different cluster members, different virtual hosts that have different personalities. So for a particular role in the cluster, that determines which container image is used to deploy the container. It determines how much CPU and memory and GPU and other resources are used by the container. It determines which services are running inside this container. So that's kind of our leverage point for dealing with the fact that different members inside the cluster may have different personalities. In this particular case, we've deployed a cluster that has a role with one member, and maybe that's some sort of controller or manager host inside the cluster. And then we have another role with 3 members running different services than the previous role. Maybe these are some sort of scale out worker task processing sort of role. It's a common setup in this sort of cluster. So all of these containers, when they come up, they're pulling a container image from some repository that's accessible to Kubernetes. And they may also be pulling in some what we call configuration artifacts. There's a set of things that is convenient to pull into the container at launch time rather than baking it into the container image, either because you want to share these among being used by different container images, or just because in the course of development or your usual processes, you revise these things and it's kind of tedious to have to bake it back into the container image each time. So when the container comes up, the application metadata may tell us that we need to pull in these extra configuration artifacts. These can be scripts that respond to lifecycle events that KubeDirector triggers. These can be things like application configuration file templates that the scripts use to help set up the application. It could be software licenses. It could be host certificates. There could be anything you want to put in this. It's just a tar file that we inject into the application at launch time. So finally, before we get into some demonstrations and details, the custom resources are really the heart of what we work with and what any custom controller works with. And there's a few custom resources already present. If you check out the KubeDirector GitHub repo today, and we're talking internally and with some other people about future features that are going to use many more custom resources. Basically, anytime you have some user-provided information that you want to be persisted, that's going to be represented in a custom resource. But to keep this particular talk focused and to try to keep us on track for allowing some questions here, we're just going to talk about the 2 main custom resources that KubeDirector will react to when it sees those created or changed in the Kubernetes resource cloud. The first one is KubeDirector cluster. And this is what represents that incoming request by an end user, or maybe by a data scientist, that says, I want to instantiate this application type. So that's the KubeDirector cluster resource. The KubeDirector cluster itself references a different type of CR called the KubeDirector app. And the KubeDirector app is that application type description, that application metadata that I've been talking about. So typically, when you're setting up KubeDirector, you would provide it with some initial set of KubeDirector apps, some initial catalog of application types that it can respond to. And maybe those will get revised or added to over time, but they don't churn a lot. The resources that come and go are instead going to be the KubeDirector cluster resources as people create and delete and modify these virtual clusters. So to talk about the details here and to demonstrate KubeDirector in action, we're going to use as a framework some of these user roles we've been talking about. This also will kind of help demonstrate if you want to set up and test out, try out KubeDirector yourself. This is kind of the set of steps you would have to go through personally to get it running. So the first user role we're going to go through really briefly, because there's not a whole lot to it, is the administration role. Basically, what do you have to do to make KubeDirector run on your Kubernetes platform? You have to create those custom resource definitions, provide those schemas to Kubernetes so it will know to be able to accept those resources through its API. You need to set up a service account for KubeDirector to use to interact with the Kubernetes API, and then deploy KubeDirector itself. And KubeDirector could technically run anywhere, but it's easy just to deploy it into a pod in the same Kubernetes cluster that it's going to be managing. And then there may be some configuration to do of KubeDirector itself. There's a few different global settings you can tweak, like which class of persistent storage should be used for the applications. But that's about it. So once you've done that, then KubeDirector is almost ready to go. You just have to make sure that then it has at least one application type specified that people can instantiate. And we'll get to that when we talk about the next user role. So let's flip over to my terminal here. So here I've got just our KubeDirector repo from GitHub actually just checked out. I've checked it out from the latest version tag, which is version 0.2. And I've got kubectl also installed here. And my kubectl client is configured to talk to a Kubernetes cluster. This Kubernetes cluster happens to be in Google Cloud, but we've run KubeDirector on Amazon, on DigitalOcean, on local hosts, on Kubernetes installed on bare metal. There's a couple of requirements that our documentation discusses, but if you want to try it out really quickly and easily yourself, I would really recommend using one of these cloud services. So anyway, I've got kubectl set up here to talk to my Kubernetes cluster, and I'm going to use this make file target that we have that's a shortcut just to help do all those administrative tasks that I mentioned in the slide. So this sets up the service account for KubeDirector. It creates those custom resource definitions that I mentioned, KubeDirector cluster, KubeDirector app, and then KubeDirector config is actually a custom resource used to manage those global settings that I talked about. Then it sends a deployment to Kubernetes that mentions the container image for KubeDirector, and we just have a container image out on Docker Hub, and my Kubernetes deployment has access over the internet to Docker Hub, so it just pulls it down, and KubeDirector is now running. If we look at the pod where KubeDirector has been deployed, we can see that it's now waiting on a particular application, a particular API namespace to see if there's anything it needs to do. So it's almost ready to go. As I mentioned, we need to now tackle the next user role, which is the application expert. So there's basically two, possibly three things that you need to provide to KubeDirector so that it knows how to deploy and manage an application. First of all, you need a container image that has the packages already installed on it. You want to have this container image as ready to go as possible. You don't want it to be downloading packages after it comes up. Just have it pre-configured as much as possible so that just once the container is launched, you can grab the final bits of runtime only information, like what's my FQDN, or what, if the user made some choices when deploying the application, what were those choices? And just apply those final choices once the container is launched. So you need to create that container image, make it available on a repository that's network accessible to your Kubernetes. And then you need to create some metadata that describes it. So obviously the metadata will have some things like an identifier and a version, bookkeeping, stuff like that. More importantly, it's going to describe what services are provided by the application. These don't necessarily have to be all services that are running inside these virtual hosts in the application, but anything that the external world will be interested in, either an end user or maybe other clusters, or any service that we might have to hook up to. In this example, I'm using Google, so I want to hook the service up to one of Google's load balancers, so it'll be externally accessible from my network. So any service that fits any of those criteria needs to be described in this metadata. It needs to, you know, have a unique label, a description, importantly, what port it's running on, and a few other things. The metadata needs to describe what roles are available in this application, and anything that is per role specific, like what container image is this role using, maybe what services are running on the virtual hosts in this role. And if you're going to use this configuration artifacts package that I mentioned earlier, there also needs to be a URL for where that can be downloaded. This is a sort of cut down example of a metadata file for Spark. This is taken from our GitHub repo. So if you go look in the deploy directory, and then under that, there's an example catalog directory, and you'll see a lot of example application types in there for things like Cloudera, Spark, TensorFlow, Cassandra. There's a plain vanilla just CentOS image to use to play around with. This is the Spark one. I've removed a few things just to make it fit on the PowerPoint a little bit easier. But you'll see that at the top level of the spec, there's a couple of properties that say, here's the container image to use, and also here's a package of configuration artifacts to inject into every container. And these are kind of global specifications for this application. They could also be overridden at the role level, although we don't do that in this example here. So on the next page here, we define just 2 roles, and there's various things that could be defined here along with overriding container image. You could specify things like minimum resources and a few other things, but the most important bits are giving the role an ID and specifying how many of the cluster members can take up this role. So in this case, we have a controller role, and there's always going to be one and only one of these in the cluster. And we have a worker role, and there can be 0 or more of those. So those are valid requests by the user. The user could not ask for 2 controllers, but they could ask for 0 or 10 workers. We don't care. Then here's a section that describes the services that are available, and particularly which port each service is running on. And finally, a config section that ties all this together. Among the defined roles, which roles are we actually going to deploy by default? And also, which services then are going to be present on each of those roles? So when KubeDirector gets a request to instantiate this application, it'll use this information to configure the network access to the different virtual hosts in the cluster. And it will also send in information about the selected role, the selected personality for each of these virtual hosts into the container itself, so that if there are scripts inside the container that are doing runtime setup, they can see which personality they've been assigned, and they may need to make decisions based on that information. So last thing to mention here, and I'm not really going to be able to do this justice, this is something that is potentially has a lot of interesting stuff going on in it, but it's kind of hard to describe in the time we have available, is the configuration artifacts. These are, like I mentioned, there could be anything you want here that you want to inject into the container after it's been launched. But the thing that we most typically have in this tar file is a set of scripts that react to lifecycle events that KubeDirector will trigger. So these are lifecycle events like, hey, you have just appeared as a new container. Do whatever you need to do on startup. They can also be lifecycle events like, another container has appeared inside your cluster in this role. Do you need to react to that? For example, if you're doing a Cassandra cluster, every Cassandra host has a config file that lists the FQDNs of other peers and seeds inside the same cluster. So if you add another host into this virtual cluster, you need to reconfigure all of the existing hosts to add its FQDN to their config files. And this sort of application-specific semantic is handled by these lifecycle hooks that KubeDirector triggers, and that runs a script that the application expert has provided when they were importing this application. And these scripts, especially the initial scripts to set things up, can get pretty interesting. But I think I'll just have to direct you to our example applications and packages and our GitHub repo if you want to learn more about that. But that's the gist of what happens with this package. So let's go ahead and, because time is moving along, let's go ahead and actually do that here. Let's go into the deploy example catalog directory. And so we have these example application type definitions here. I'm going to send this one to Kubernetes. And then it will exist there to be referenceable by KubeDirector when someone asks to instantiate this kind of application. So finally, we come to the end user, and the end user's job is, by design, pretty simple. We want to give the tools as much as possible to let the administrators and the application experts bake in all the complexity into a policy that the end user can then just say, give me one of those, and not have to like decide what container image to use or how many resources to apply. In this case, this is a completely valid request document for instantiating a Spark cluster. There are other things you could add to this request to make it more complex, but this sort of request here will work. And all this is saying is that for the controller role, I do want to limit the memory to 4 gigs, so I'm adding that into the request. And then for the worker role, I want 2. So that's all I'm really saying is the end user. Rather than spend time talking through these diagrams here, I'm just going to see if I can sort of do a play-by-play of what KubeDirector is doing when we try this out in practice. So again, in the deploy directory, we have this example clusters subdirectory, which has a bunch of example instantiation requests that you could use to throw at KubeDirector. I'm going to do, this is a slightly simpler version of the example Spark cluster. So it's pretty similar to what we saw on the PowerPoint slide, except that it's being a little more restrictive about the CPU and memory resources that it's asking for. So I'm going to give this to Kubernetes. And once this document has been persisted in the Kubernetes data store, KubeDirector will notice it and will start doing things. So let's go back and look at the KubeDirector logs. So if we start here at this line I'm highlighting, we can see that it's noticed there's a new document that's requesting an application of this Spark type that we defined earlier. And this document says we have a controller and worker role, and we've validated those as valid roles for the Spark type. And we've created a stateful set to represent each of these roles and set its replica count for the stateful set to the number of members that have been requested for each of the roles. Then we have gone into the containers and injected just a JSON file that completely describes the request and kind of the current state of the cluster, the FQDNs, the services, anything that a setup script, one of these lifecycle reaction scripts inside the cluster might need to know in order to do its job. So we've injected that file into the cluster, and then because there was this configuration artifacts package mentioned in the application metadata, we've pulled that down over the web, injected that into each container, and run the script for new container. You're starting up as a new container, do whatever you have to do. And so that script has the Spark specific knowledge in there that our Spark application expert provided to take this cluster configuration information and do final setup, whatever is necessary to make sure that the Spark master knows what it's doing and that the Spark workers are connected to the Spark master. So that's what you see here when it says running app config setup and running app config in these pods that it's creating. And then as part of this state machine, this reconciliation loop, it has triggered this configuration, and then it goes away. And then it comes back later and says, are you done with configuration yet? And in this case, no, the initial configuration is still ongoing. One other thing I probably should mention here is our request mentioned some persistent storage for the controller role. So it asked for 40 gigs of storage. One of the things that KubeDirector will do in this case is it will bring up a persistent volume attached to this particular container. And depending on the application metadata, that application type will specify which directories in the file system of the container image actually need to be persisted. And so we will copy the initial state of those directories, like maybe it's /opt or maybe /data. You know, you don't care about all your binaries in /bin. Those aren't going to change. If your container goes down and comes back up, you can just start fresh from the container image. But there may be other directories that you really do care about any changes in persisting them. And so we will copy the initial state of those directories over into the persistent volume and mount those back at their usual location inside the container. And then any changes to those directories will be written to the persistent volume. And so we'll see that here in just a second. Let me see if, so KubeDirector is done doing all the things it's going to do. If we do a, whoops. And let me actually do describe rather than get, because if you do a describe, you'll get the events that have been posted as well. So this is the type of object that we created, and there's only one of them, so it's only going to list this one object. And so this is our custom resource. This is the request we sent to Kubernetes. So if we look at the spec, this spec is essentially the document we passed in. It just persisted what we asked for. You'll notice that there's a few other things that have been populated that were not included in our initial spec. There's like the storage class name. There's the service type. These are some defaults that got filled in because we didn't specify something different. So the spec part is not that interesting. That's not going to change until we change it. Maybe the more interesting part is the status section. And the status section really communicates two things. One is the overall state of the cluster, like is it in some sort of transitional change or is it ready to go? And the other is all the different objects that have been created on behalf of this custom resource. So for example, the controller here has a persistent volume claim. If we wanted to inspect that, we could see what Kubernetes object was set up there. I'm going to skip ahead kind of to the punchline here in the interest of time and look at this service for the controller. So service object in Kubernetes is a representation of a collection of ports. And we use it to say, for this particular virtual host, what are all the externally accessible service ports that we need to deal with? So we've defined like port 22 for SSH, port 8080 for the Spark Master Web UI. Actually, let's look at that one. So this service is telling us that for our controller node, if we were to go to, and this is the virtual controller of our virtual Spark cluster that we just created. If we were to go to this IP of a Google load balancer and look at port 8080, we should see our Spark Master Web UI. So let's go ahead and try that out. So yeah, there it is. You can see that it's reporting 3 workers. That's because in this particular setup, we have put a Spark worker on the controller as well. So there's the Spark worker on the controller and then the 2 extra workers we asked for. If we go back to our request, let's edit our request a little bit. And remember, we're just sending a change in a document to Kubernetes, and then KubeDirector is responding to that change and interpreting our change document as a request to change the cluster. So we've increased the worker count from 2 to 4. I'm going to apply that change. And then we can, let's describe our object again to look at the events. So we can see on the events that are being posted to our cluster object, it notices that we're expanding the role from 2 to 4. And so it's reconfigured the stateful set to have more replicas, and it's waiting for those pods to come up. When those pods do come up, it's not only going to trigger the lifecycle event for new container inside those pods, it's going to go into all the existing containers and trigger the lifecycle event for there's been a new member added to your cluster. And so if this application has a script that reacts to that, it can do that as well at this time. So the containers have come up, it's running those lifecycle event scripts, and now it's stable again. So if we were to go to this user interface and reload it, we can see we have 2 more Spark workers that have come up. So let me skip past these guys. These are images and also with a lot more descriptive text on our wiki. I think we're pretty much done at this point. I really, I hope we've illustrated these first two key takeaways, and I really encourage people to have a look at our GitHub repo, not only the wiki, but also the other documentation there. There's, I think, a pretty good quick start document for how you can just clone the repo and instantly run KubeDirector. I did see out of the corner of my eye another question about whether we can use KubeDirector with AWS or GCP, and the answer is almost certainly yes. We've tried it with AWS, Google, DigitalOcean, I think some other cloud service. There's just a few requirements for what sort of Kubernetes you want to deploy to, and once those are met, we should work anywhere. But I think I'll call it at this point, see if Tom has any closing remarks he wants to make, and then we can squeeze in a few more questions.
Thanks, Joel. I've been answering some of the questions that we've been going along, but there are two questions I think we could probably address live here. There's a question about monitoring the application running within the Kube Director, so the application that's being deployed. Is there any functionality that we have available that determines whether the application has failed and how it can be restarted, that sort of thing?
Yeah, so not currently.
Right.
This is the category of things where we want to make sure we have the architecture to address this going forwards. So, Kubernetes has the idea of health checks that you can define for containers, and that may be sufficient for a lot of cases. But if you want, if you need a more detailed set of examinations that need to be done in order to determine exactly what's up and what's down and what's going wrong, then that again is some application-specific semantic that would have to be provided in this package of importing the application to KubeDirector. And I think the way we're talking about approaching this, a lot of the concepts that we're doing with KubeDirector are things that we kind of test bedded with our application called Epic, our management platform, where we do a lot of this same sort of data-driven application deployment. And one of the things we have there is we have an agent that we can insert into the clusters that can watchdog the defined services, these services that are presented in the metadata, and report service status all the way back into the management controller. What we're talking about doing for KubeDirector is not injecting agents into the containers, but rather having like a sidecar container inside the same pod that can do all sorts of things, really. One of the things, though, that it could be good for is monitoring status and reporting status back to KubeDirector, where it can then be written into the status section of the custom resource. But it doesn't do that right now. It's just things we're talking about for the future.
All right, thanks, Joel. The other thing I want to talk about a little bit is the use of existing application operators. So does this require the use of KubeDirector? Does it require a complete rewrite? My answer is no. You can take the existing application operators and wrap them with the additional functionality of KubeDirector. Is that correct, Joel?
Yeah, you could. It would really be a case-by-case
right.
Question of whether that would be the way you'd want to approach it. It might be easier just to start with just the normal packages for installing the application and write the KubeDirector metadata directly.
Okay. Good. And for the final question before we turn it back to Caitlin, is there was a question around Knative. Okay, so Knative is kind of the tool that Google has released that allows stateless applications to inherit some common functionality. Is there anything equivalent to that in KubeDirector?
Stateless applications to inherit common functionality.
Well, so for example, if with Knative, if you have a stateless application, you automatically inherit the ability to auto scale, for example, and other sorts of functionality like that. The question
okay, got it. Yeah. So this comes back to what I was talking about the benefit of having a single manager with a data model and an operations model that encompasses not only how to deploy and manage application types, but also other features. Like there's an auto scale feature that we're working on in Epic right now that we like many things, we'll be thinking about how to represent that in KubeDirector. That allows you to specify, load-based policies for particular roles for particular hosts and particular roles within a cluster. And so it's kind of an application agnostic way of specifying an autoscale policy that interacts with the way the application is modeled to KubeDirector. So, for example, in that sort of regime, if you've modeled the application correctly, if you've given KubeDirector a valid application metadata, then it automatically gets the benefit of being able to work with an autoscale policy like that. So again, I'm kind of hand waving that because this is future work, but it's definitely the sort of thing that we're trying to enable through this approach. Is get all the goodness of having these data-driven ways of talking about these applications, and that lets us build processing pipelines and build interactions with corporate services like Active Directory in ways that can then automatically apply to any application that's imported into KubeDirector.
Thanks, Joel. I think that's about all the time we have for questions. I know there's a few more. We'll try to get back to you on those. Caitlin, back to you for a wrap up.
Awesome. Yep, we are coming right on the top of the hour here. So thank you so much, Tom and Joel, for the great presentation, and to everybody who joined us today and asked those great questions. The webinar recording and slides will be online later today, so look out for those. And we look forward to seeing you at a future CNCF webinar. Have a great day, everyone.